When most students first see the periodic table, it can look like a confusing collection of letters, numbers, and boxes. But there's actually a tremendous amount of information packed into one table. The periodic table isn't just a list of elements. It's a system of organizing and classifying matter, and once you understand how that system works, you can begin to predict how elements will behave. In this video, we're going to take a closer look at the periodic table and learn how to read it. So rather than simply memorizing the periodic table, let's learn how to read it, understand it, and use it. Before we start with the structure, there are a few things students need to understand before looking at the classifications. First of all, the atomic number. What it means and why elements are arranged by it. The periodic table is arranged by the atomic number, which is the number of protons in an atom's nucleus, because this fundamental property determines an element's chemical activity and its identity and electron configuration. While earlier tables used atomic mass to order the elements, which created inconsistencies where elements with similar properties do not align correctly. This problem was solved when scientists learned how to measure the number of protons for each element, the atomic mass. This is the sum of the protons and neutrons' masses and atomic mass units. Because electrons have very little mass, they're generally excluded from this calculation. Notice this is not a whole number, but rather a weighted average of all known isotopes and their percent occurrence in nature. Okay, moving over to the chart now. Each row is called a series or period. So the horizontal rows will be numbered 1 through 7. So it'll be 1, 2, 3, 4, 5, 6, and 7. The columns are called groups or families. So elements in a group have similar chemical properties. Okay, notice at the bottom down here we have what is called the lanthanide and actinide series. Why are they placed here separately at the bottom? Well, they're placed separately at the bottom primarily for practical layout and readability. If included in the main body of the table, it will become excessively wide. So it spans from 18 columns like it is here to over 30 columns, making it unwieldy for textbooks, posters, and screens. And there's some key reasons for this separation, besides this space efficiency. These are known as the F block elements, and we'll talk about those later when we start talking about electron configurations. Not only for space efficiency, but it also, these 14 elements are contained within the F block of elements of intertransitional metals. They're very similar in chemistry, allowing them to be grouped together without disrupting the periodic trends of the main transition metals. And many of these elements were discovered much later and are often radioactive or synthetic, warranting a distinct grouping that highlights their unique properties without cluttering up the main table. Although displayed separately, they technically belong to period 6 and period 7. Okay, let's discuss how the groups are named and numbered. The first column are called the alkali metals, the first family. The second one is called the alkaline earth metals. This midsection here, this is called your transition metals. Then we have the boron family, the carbon family, nitrogen, oxygen families, the halogens, and the noble gases. Now, think of hydrogen as being an oddball here, because hydrogen is not really a metal. Okay, so you may want to distinguish that by maybe separating the hydrogen here from the rest of them. Let's look at the numbering scheme. Notice there's two different sets of numbers. The newest, most modern system is the IUPAC method, where each column is numbered numerically from left to right, from 1 to 18. The older system, used primarily in the United States, is the CAS or CAS system, or the AB numbering system. Okay, the letters A and B in the older periodic table systems serve to distinguish between main group elements and transitional elements. So the A group, or the main group, will be the first two columns and the last six columns. That's the main group. So they get the A designation. The transitional metals all get a B designation. All right, groups 3, 4, 5, 6, and 7B, they're related to valence electrons. So this has 3 valence electrons, 4, 5, 6, and 7 valence electrons. And the next group, group 8, is a triad. This is a unique group containing iron, cobalt, and nickel to form the triad. In the CAS system, iron, cobalt, and nickel families form a unique triad of elements with exceptionally similar chemical and physical properties. Elements in these 3 columns share striking similarities. For example, oxidation numbers. Their oxidation numbers are +2 or +3 primarily, unlike their neighbors, which are like +6 and +7. Physical properties. Iron, cobalt, and nickel are the only elements that are ferromagnetic at room temperature. And each group of 3 here horizontally are very similar in properties, very similar to a vertical homolog. So this horizontal similarity was a strong reason that they were all placed together into one category, group 8B. Groups 1B and 2B on the right side of the transition block, because these elements have 1 and 2 valence electrons respectively in the outermost s orbital, completing the d block sequence. Okay, the metals are on the left of this vertical staircase. All right, so going into the left, we can classify the metals as good conductors of heat and electricity. They're usually shiny or have luster when cut. They're malleable, which means they can be hammered into a thin sheet. Ductile, which means they can be drawn into a thin wire. They're usually solids at room temperature. They tend to lose electrons and form cations. The nonmetals are to the right of this staircase. They're generally considered poor conductors of heat and electricity, often dull, brittle when solid. There are many gases. They tend to gain or share electrons, and they form anions or covalent compounds. Metalloids are the ones I have shaded here. This is where the periodic table gets interesting. Separating the metals from the nonmetals, they have properties intermediate between those of metals and nonmetals. They're called semiconductors, which gives you a great real-world connection. So silicon, germanium, arsenic, they're used in most modern equipment. Okay, modern equipment depends upon these 3 elements. So where are the solids, liquids, and gases located? Okay, so let's start with gases. So hydrogen is a gas, nitrogen, oxygen, fluorine, chlorine, and then these. Okay, so these are all the gases. What about the liquids? Okay, the liquids will be mercury. Mercury is liquid. And bromine is a liquid. All the rest are solids. So it's easy to find them because gases are low molecular weight nonmetals. Most metals are solid, with the exception of mercury. And there's one nonmetal, which is a liquid, which is bromine. The others are solids. Radioactivity is a property of particular isotopes, not simply an absolute property of an element. An element is radioactive when its atomic nucleus is unstable, meaning the forces within the nucleus are unbalanced. This instability is particularly caused by the imbalance of neutron to proton ratio, or having too many protons and neutrons. Typically, the elements with atomic numbers greater than 82 are considered, okay, so here, so these are considered radioactive. Also, cadmium is considered radioactive, along with promethium. Most people, when they think of radioactive materials, they think mostly of uranium, maybe thorium, plutonium. Okay, let's describe the families of elements in more detail. So we can say that the alkaline metals, they are very low density. In fact, they float in water. They have one valence electron that they will lose very easily, resulting in a +1 oxidation state. And they're extremely extremely reactive, especially with water. And they're never found in pure form. Alkaline earth metals, similar to alkaline metals, they're harder, they're denser, they have a higher melting point than the alkaline metals. They have two valence electrons, they form a +2 ion, and they react less violently than the alkaline metals, and also they're never found in pure form. Like, you're never going to dig up calcium, for example. It has to be a calcium salt because they're too active to exist by themselves. The transition metals, they're hard, dense, shiny solids with high melting points, high electrical conductivity. They exhibit a range of oxidation states and are generally less reactive than groups 1 and 2. Your halogens are highly reactive nonmetals with 7 valence electrons that are aggressively seeking to gain one more electron, resulting in a -1 oxidation state. They exist as diatomic molecules, which means they exist as two atoms combined together, such as F2, Cl2, etc. And they're also never found in their pure form because they're too reactive. Okay, your noble gases have a full valence shell of electrons, making them monatomic, colorless, odorless, with virtually no chemical reactivity and the highest ionization energies. Metalloids display intermediate between metals and nonmetals and often act as semiconductors. And here's a group that a lot of textbooks do not really go into any detail, and that's reactive nonmetals. This includes carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur, and selenium, which is the upper right-hand portion of the periodic tables, not including the halogens, with one exception, which is hydrogen. As you will learn later, electrons are packed into different blocks. Okay, the S block is located here. This is the P block, excluding helium, because helium is in the S block. So you can think of helium as sitting over here next to hydrogen. But all the rest of these are in the P block. The transitional metals will be in the D block. In this region, this is the F block. So this is valuable for chemistry students because it explains why the periodic table has the shape it does. It isn't shaped this way because someone thought it looked nice. Its shape reflects the arrangement of electrons in atoms. Okay, so we can say then that there's one valence electron in group 1. There's two valence electrons here in group 2. In group 13, there's 3. 14 has 4. 15 has 5. 16, 6. 17 has 7. And 8 with the exception of helium. You can also classify elements according to the way they tend to do things chemically. For example, we can say that metals tend to lose electrons, so metals are electron donors. We can say that nonmetals tend to gain electrons, so they're electron acceptors. Many nonmetals form covalent bonds by sharing electrons. Metals plus nonmetals form ionic bonds. So you can think of nonmetal plus nonmetal as completing to form a molecular or a covalent bond. Did you know that humans actually made some of the elements? So we have some elements that are naturally occurring and some are synthetic. A list of the synthetic elements, we'll start at element number 95. So starting at element number 95, okay, so those are synthetic or man-made, and continues here. We have two elements that are considered synthetic because they do not occur with any significant natural quantities. In other words, they're very, very, very rare. Okay, so that would be number 43, technium, and number 61, promethium. They're considered synthetic because they do not occur in any significant natural quantity. Neptunium and plutonium are sometimes called synthetic, although they have been found in nature, but also they're not very common. So now you know where the man-made elements are located, but where does the periodic table end? Many scientists estimate the table effectively ends at around element 120, because synthesizing heavier nuclei becomes exponentially difficult due to extreme instability and short half-lives. Theoretical models also predict an island of stability centered around element 126, where super heavy elements might have longer lifespans, potentially extending the table to possibly element 164 or beyond if these stable configurations are achieved somehow. Okay, something interesting will be the abundance of elements. For example, in the Earth's crust, there are 8 most common elements are listed as oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium, where oxygen occupies about 46%, give or take. Silicon's about 27-28%. Aluminum, about 8.1%. Iron, around 5%. So on and so forth, decreasing down to magnesium, which is about 2.1%. In the atmosphere above us, most of the atmosphere contains only 3 gases: nitrogen, oxygen, and argon. So together, all 3 of these is about 99% of all the elements in the atmosphere. You probably remember that nitrogen is around 78%, oxygen is around 21%, and argon is around 1%. Now, in the oceans, by mass percentage, it's primarily oxygen and hydrogen, with oxygen being about 85%, 86%, and hydrogen being about 10 or 11%. By mass dissolved, then we have like chlorine, it's like almost 2%. And going down to potassium, which is about 0.04%. So those are the most common dissolved elements. All right, the rare earth elements. Rare earth elements are all chemically similar. They're silvery white metallic elements that are critical for modern technology, including electric vehicles, smartphones, and defense systems. The group consists of 15 lanthanides plus scandium and yttrium, which share chemical properties that are often found in the same ore deposits. Despite their name, these elements are not actually rare. However, they are rarely found in concentrated, economically valuable deposits and are difficult to separate and purify due to their geochemical similarity and a tendency to be mixed with other elements like uranium and thorium. So you can see the periodic table is much more than a chart that tells us the names and symbols of the elements. The periods and groups tell us where an element belongs. Its location can tell us whether it's a metal, non-metal, metalloid, which family it belongs to, how many valence electrons it has, and even give us clues about how it will react with other elements. We can also use a table to identify solid, liquid, and gaseous elements, distinguish between stable and radioactive elements, and recognize the main group, transition, lanthanide, and actinide elements. And once you understand the organization of the table, you begin to see something really important. The properties of these elements aren't random, there's a pattern. That pattern is what makes the periodic table such a powerful tool in chemistry. In upcoming lessons, we'll use these patterns to explore periodic trends, electron configurations, chemical bonding, and behavioral elements in chemical reactions. So don't think of the periodic table as something you simply have to memorize. Learn how to read it and let the table do some of the work for you. Thank you for watching. If you found this video helpful, please be sure to check out other lessons on this channel. Please leave a comment, like, and subscribe. Thank you for watching.